Hey friends, welcome to the YouTube channel all about electronics. So in this video, we will learn about the common base amplifier. So if you have followed the last couple of videos on the BJT, then we have discussed about the common emitter and the common collector amplifier. So similarly, now let us talk about the common base amplifier and let us find out the different amplifier characteristics like the voltage gain, the input and the output impedance. So without directly jumping on the actual circuit of the common base amplifier, let me start with the very elementary circuit and then step by step we will see the actual circuit. So this is the very basic circuit of the common base amplifier. So here this AC input signal is applied at the emitter terminal while the output is measured at the collector terminal. And for a moment let us assume that some DC biasing voltage is already applied at the base terminal. So for the AC signals, these DC voltage sources will act as a 0. That means now this base terminal will act as a AC ground. That means now if you see, the input signal is applied between the emitter and the ground terminal, or effectively between the emitter and the base terminal. Similarly, the output is measured between the collector and the ground terminal, or effectively between the collector and the base terminal. That means in this configuration, the base terminal is common between the input and the output side. And that is why this amplifier configuration is known as the common base amplifier. Now normally when we connect the input signal, then we apply it through the coupling capacitor, right? Because through the coupling capacitor, we can isolate the AC and the DC signals. So if we connect the input signal as shown in the figure, then let us see what happens. So when we apply the input signal in this fashion, then we know that for the DC signals, this coupling capacitor will act as an open circuit, right? So because of that, there won't be any path for the biasing current, because here the emitter terminal will act as an open circuit. So because of that, there won't be any bias current and there won't be any output signal. That means there has to have some path for the biasing current. So let's provide the path for the biasing current. And let's connect the input signal in this fashion. And let us see whether this circuit will work or not. Now in this circuit, although there is a path for the DC biasing current, but for the AC signal, this coupling capacitor will act as a short circuit. And because of that, here the input signal will also get grounded. And due to that, we will not get any output signal. So it shows that if you want to couple the input signal, then there has to have some series resistor at the emitter terminal. So this is the proper way to couple the input signal at the emitter terminal. Now so far we have assumed that there is some biasing voltage which is already applied at the base terminal. But now let us see how to bias this base terminal. So for the biasing, we can apply some fixed biasing voltage via the base resistor, or even we can use the voltage divider bias. And first of all, let us discuss this circuit, where the base terminal is biased to the fixed voltage via the base resistor. So here our aim is to find the different amplifier characteristics like the voltage gain, the input and the output impedance. And we know that for that we need to do the small signal analysis of the given circuit. So for the small signal analysis or for the AC analysis, we will consider all the DC sources in the circuit as 0 and we will replace the coupling capacitors by the short circuit. And then after, we will replace the BJT by the small signal model. So if you see over here, this emitter resistor is connected between the emitter and the ground terminal. So in the equivalent circuit, it can be shown like this. Now here, this input signal is also applied between the emitter and the ground terminal. While if you see this base resistor RB, then it is connected between the base and the ground terminal, while this resistor RC is connected between the collector and the ground terminal. So this is the AC equivalent circuit of the common base amplifier. And using this circuit, let us find out the voltage gain, the input impedance and the output impedance. And first of all, let us find out the voltage gain. So here, this current is the collector current, right? So we can say that this output voltage Vout is equal to minus IC times RC. Or we can say that it is equal to minus Gm times V pi times RC. So here, to find the voltage gain or the Vout divided by Vin, we need to find the expression of the V pi in terms of the input voltage. Now if you see over here, this resistor R pi and the RB are connected in the series connection, and that series connection is connected in parallel with the input signal. So from this we can say that this voltage V pi is equal to minus Vin times R pi divided by R pi plus RB, because here the polarity of the voltage V pi is opposite to the input voltage, right? So now let us put this value of V pi in the earlier expression. That means voltage Vout is equal to minus Gm times V pi times RC, or we can say that it is equal to minus Gm times RC times minus Vin times R pi divided by R pi plus RB. That means Vout is equal to Gm times R pi times RC times Vin divided by R pi plus RB. Now here this Gm times R pi is nothing but the beta, right? Because R pi is equal to beta divided by Gm. So from this we can say that voltage Vout divided by Vin, or the voltage gain, is equal to beta times RC divided by R pi plus RB. And if we divide the entire expression by the beta, then we can say that this voltage gain is equal to RC divided by R pi divided by beta plus RB divided by beta. And this R pi divided by beta is equal to 1 over Gm. That means this voltage gain is equal to RC divided by 1 over Gm plus RB divided by beta. But if this base resistor RB is 0, in that case this voltage gain is equal to RC divided by 1 over Gm. So it indicates that if there is any resistor between the base and the ground terminal, then it will get divided by the factor of beta, and it will get added with the 1 over Gm in the denominator. So this is the expression of the voltage gain. And if you see over here, then there is a no negative sign, which indicates that the input and the output signals are in the same phase. And here, if this base resistor RB is 0, in that case this voltage gain is same as the common emitter amplifier, that is equal to Gm times RC. But because of this base resistor, the voltage gain reduces. So at the later part of the video, we will see that how we can nullify the effect of this base resistor and how we can improve the voltage gain. Alright, so similarly, now let us find out the output impedance. So the output impedance is the Thevenin's equivalent impedance which is seen from the output side. And for that, we will consider all the independent sources in the circuit as 0. That means we will consider this input voltage source Vin as the 0. That means we can replace this input voltage source by the short circuit. So once this input voltage source gets short circuited, then this emitter resistor will also get short circuited. Also, if you see over here, this series connection of the R pi and the RB are also connected in parallel to the input voltage source. That means once the input signal gets short circuited, then these two resistors will also get short circuited. And with that, the voltage V pi will also become 0. That means this dependent current source will also act as an open circuit. That means now, if we see the Thevenin's equivalent resistance from the output side, then it is equal to RC, or we can say that the output impedance is equal to RC. So similarly, now let us find out the input impedance. So if Vin is the input signal and the In is the input current, then the ratio of this input signal to the input current will give us the input impedance. And to find that, let us apply the KCL equation at this node. So here, this current is the base current, while this current is the collector current. And here let us assume that the current which is flowing through this resistor Re is equal to IE dash. So if we apply the KCL, then we can write current In plus IB plus IC is equal to IE dash. Now here, this current IB is equal to V pi divided by R pi, right? That means we can write this expression as current In plus V pi divided by R pi plus Gm times V pi is equal to V in divided by Re. So this IC is equal to Gm times V pi, while this current IE dash is equal to V in divided by Re, right? That means from this we can say that current In is equal to V in divided by Re minus Gm times V pi minus V pi divided by R pi. That means current In is equal to V in divided by Re minus V pi times 1 divided by R pi plus Gm. Now we know that this R pi is equal to beta divided by Gm. That means 1 over R pi is equal to Gm divided by beta, and definitely it will be much less than the Gm. That means here we can neglect this term. So neglecting this term, we can write this current as In is equal to V in divided by Re minus V pi times Gm. So here we need to find the expression of the V pi in terms of the input signal. And earlier, as we have seen, this voltage V pi can be given as minus V in times R pi divided by R pi plus Rb. So let us put the value of V pi in this expression. That means current In is equal to V in divided by Re plus V in times Gm times R pi divided by R pi plus Rb. Now we know that this Gm times R pi is equal to beta. That means current In is equal to V in divided by Re plus V in times beta divided by R pi plus Rb. That means current In divided by V in, that is the 1 over input impedance, is equal to 1 divided by Re plus 1 divided by R pi divided by beta plus Rb divided by beta. So here basically we have divided the entire expression by the beta. So from this we can say that 1 over input impedance is equal to 1 divided by Re plus 1 divided by 1 over Gm plus Rb divided by beta, because this R pi divided by beta is equal to 1 over Gm. So from this we can say that this input impedance is the parallel combination of Re and the 1 over Gm plus Rb divided by beta, right? And if this base resistor Rb is 0, in that case this input impedance is the parallel combination of Re and the 1 over Gm. So in this way we got the expressions of the voltage gain, the input impedance and the output impedance of this common base amplifier. Now instead of this fixed bias, if the base is biased using the voltage divider, then the equivalent circuit can be drawn like this. So here this Thevenin's equivalent voltage Vth can be given as R2 divided by R1 plus R2 times Vcc, while this Thevenin's equivalent resistance is the parallel combination of R1 and the R2. So now if you see this circuit, then it looks similar to the fixed bias circuit. And for this circuit, the expressions of the voltage gain, the input and the output impedance will also remain almost same. But here the resistor Rb will get replaced by the Rth. That means now the voltage gain is equal to Rc divided by 1 over Gm plus Rth divided by beta. Similarly, the input impedance is the parallel combination of Re and the 1 over Gm plus RTH divided by beta, while the output impedance is equal to RC. So as you can see, because of this base resistor between the base and the ground terminal, the voltage gain reduces. And we can improve the voltage gain by connecting the bypass capacitor between the base and the ground terminal. So for the AC signal, this capacitor will act as a short circuit, and because of that, the base terminal will get grounded. That means using this bypass capacitor, we can improve the voltage gain. Now here, the value of the capacitor should be selected in such a way that at the operating frequency, it will act as a short circuit. Now, so far we have seen that if there is any resistor between the base and the ground terminal, then it will appear as R divided by beta in the voltage gain as well as the input impedance expression. That means in these expressions, it will get connected in series with the 1 over Gm. So if we want to nullify the effect of this term, then this R divided by beta should be much less than 1 over Gm. Or in this case, the reactance divided by beta should be much less than 1 over Gm. So practically, this Xc divided by beta should be at least 1 by 20 times 1 over Gm. So if this condition gets satisfied, then we can assume that at the operating frequency, this capacitor acts as a short circuit. So while selecting the value of the capacitor, this criteria should be kept in the mind. So if we use this bypass capacitor, then the input impedance of this common base amplifier can be given as 1 over Gm in parallel with Re. Now usually, the value of Re is much greater than 1 over Gm. So because of that, we can say that the input impedance is approximately equal to 1 over Gm. That means for this common base amplifier, the input impedance is very low. So the question arises, what is the use of such amplifier when the input impedance is very low? Because normally we say that the input impedance of the amplifier should be high, right? Well, at the high frequencies, these amplifiers can be used for the impedance matching with the transmission lines. Because for these transmission lines, the characteristic impedance is in the range of tens of ohms. So that is one such application where these low input impedance amplifiers can be actually used. So that's it for this video, and I hope in this video you understood about the common base amplifier. So we will take some examples based on this common base amplifier on our second channel. So do subscribe to that channel also to get the regular update about the various quiz. So if you have any question or suggestion, do let me know here in the comment section below. If you like this video, hit the like button and subscribe to the channel for more such videos.